Okay, now I'm actually going to get started. So today we're going to go real quick over the midterm. There you go. Today we're going to go real quick over the midterm. Let's see. So there was a numerical homework that was due today, but only like half of the people, maybe 3/4 of the people did it. So I figured I'd just make it due Monday. So do the numerical homework for Monday. I don't care too much about it when it's due, so that's fine. So do the numerical homework for Monday. I didn't make a big deal about it. I don't think that I even mentioned last week that there was a numerical homework due, so I'm not super worried. So do it for Monday. We'll talk about it Monday. There's a reading. Reading 7 is now due for Monday, so due Sunday. For both of these things, Sunday night, I mean. Like midnight, the very first thing, first minute of Monday is what I mean by due Monday. So I want to see them, yeah.
You have your Monday listed as Monday night at 11:59. You want to keep that or?
On which one?
The reading.
I think I changed that one like 2 minutes before class.
Okay.
So double check. Just get everything done Monday morning.
Okay.
And I will fix it if it's not right. So today we're gonna go over. Maybe I'll put that over here. So the first problem, sketch an HR diagram. Make sure to include the vertical axis with units, the horizontal axis with temperatures, and stellar classifications, and the main sequence, and red giants, and white dwarfs. And I don't really have anything to comment on this because I think everybody basically did what I wanted. I was pleased with that. So that's great. So the HR diagram, the reason that I spent time on the HR diagram, and the reason that I care about it is what we're going to do for a large part of class. Oh, I forgot to put the screen down. What we're going to do for a large part of the next sections of class is go through how things move around on the HR diagram and how do you actually get something specific positioned on the HR diagram. So the HR diagram is more than just a cataloging of stuff. We can understand the physics of stars through the HR diagram. So we'll come back to that quite a lot. Okay. Let's do some just basic astronomy. Betelgeuse is a large red star that we hope to blow up sometime in our lifetime, but we know we're not going to get that lucky. It has a temperature of 3,600 Kelvin and a radius of 1,000 solar radiuses, and it is a distance of 168 parsecs. This is pretty straightforward. It's a problem just like one you did in the homework. The bolometric luminosity. So there's several ways to do this because astronomy is a really old field. So sometimes you'll see the bolometric luminosity is clearly defined. The magnitudes are a little tricky because there's been some changes over the years. And so in 2015, the International Astronomical Union, the IAU, which is the people who really decide all this stuff, said that for a magnitude 0, so if the total bolometric magnitude equals 0, then the bolometric light luminosity is this number, 1.3 times 10 to the 31 watts. And I'm going over here just so I write down the right number. 3.01, because I got it backwards, that's why I looked it up, times 10 to the 28. So they made this relationship, and what that does is that says that the bolometric magnitude is just minus 2.5 times the log base 10 of the total luminosity over this fiducial luminosity. Now, this happened after the book came out by like 6 years, 7 years. One of the ways that the book says, and other ways that you might find things in the literature, is the bolometric magnitude is the magnitude of the sun minus 2.5 times the log base 10 of the luminosity of the object divided by the luminosity of the sun. Which is related. Like, this is a similar thing. It's just instead of using this L naught, we're using the luminosity of the sun, and we need to compare it to the magnitude of the sun, which is like minus 4. So this is the one. This is the way you ought to do it. But some people did this, which is also fine as long as you use a solar luminosity and not this number. This number is good for a star with a magnitude of 0, which is a very bright object. Okay, that's all I need to say about that one. Let's see. The next thing that I asked for was the apparent brightness, which you get from the absolute magnitude. So that wasn't what I asked first. What I asked first was the bolometric luminosity. And this is just A sigma t to the 4th, where A is the area, 4 pi r squared. Sigma is a number that you get from this horrible integral that I didn't make you do. And t to the 4th is t to the 4th. I think everybody did that properly. The distance, was that?
Isn't there like an R?
Sure. But I gotta erase the A.
Oh, okay.
So you can call this 4 pi r squared. Just a surface area. Just the total
Okay.
surface area. So the distance modulus is just little m minus big M. And, okay, so these little m and big M are actually different objects, even though they're both m's and they're both dimensionless. Because big M is the total luminosity coming off the object, and little m is that luminosity divided by the distance. So that's why the distance modulus is because it gives us these two guys, and then you can find the actual distance as 10 to the mu over 5 plus 1. Which I didn't ask you to do. And then the apparent magnitude you get from this. So you know what the distance modulus is. You can get the apparent magnitude from the distance modulus and the total brightness. And I think everybody, I think I didn't take off very many points for that one. 5 was a little rougher. Where's my... I thought I fixed that. I thought I wrote the solution. Where'd it go? Let us go look. So the last one was about I like that it makes noise up there. That's hilarious. Okay, is that better? Yeah, there it is. Okay. So the third problem was about Boltzmann. Where'd my eraser go? Set it down. So the third one says we've got a cloud of hydrogen gas at a certain temperature T. At what temperature is half the population in the first excited state and half in the ground state? Every single one of you made the same mistake. Well, okay, half of you anyway, made the same mistake. I only took off a point, so don't worry too much about it. But if half the population is in the first excited state and half is in the second excited state, so N2 or N1, this is a half, and this is a half. So this ratio is 1. A lot of you had an extra log of 1/2 kicking around in your answer. This equals G2 over G1 times e to the minus E2 minus E1 over KT. So now we're looking for the temperature. So we have to do this, so we have to do a little bit of algebra to get the temperature. So we get the E by itself. So we have G1 over G2. And what is that? That's equal to a quarter, because G2 is 2 times 2 squared, and this one is 2 times 1 squared. So this is just 4. When it's upside down, this is just 1/4, which I'll care about in a second, but right now I'm going to leave it as the G's. Equals this, so we take a log of both sides. I take a log of that, and I'm left with minus delta E over KT. Working with logs is a good way to make a mistake, so make sure you're careful there. And then I move the T over here and the log over here, and I'm getting that T equals minus delta E over k times the log of g1 over g2. So, so delta E, how do you get delta E? Delta E is 13.6 times 1 over 1 squared minus 1 over 2 squared, because the energy of the nth level is minus 13.6 times n to the minus 2. I think this is stuff that everybody's good, solid on. So delta E is 10.2. And the log of G, this is the log of a number that's smaller than 1, and logs of numbers that are smaller than 1 are always negative. That's where this minus sign goes. So if you have this thing upside down, then that's where you picked up a minus sign. Or if you did your energy difference in the wrong order, you pick up a minus sign there. So then you get about 85,000 Kelvin. Does anybody have any questions about that? Are you guys good?
Yeah. Wait.
Yeah.
The one problem I had was the G1 and G2 values.
Yeah.
Like, what do you put into those?
So G1, so that is the degeneracy, and it is set by the number of electrons you can cram into an orbital.
Oh. So for most of them, is it 4?
No,
No.
it's n squared. It's 2n squared. Sorry, my camera's wrong. Now you go on. There you go. So you have these orbitals. So when I have here's my nucleus, and then I've got my n equals 1 orbital, and I can fit 2 electrons in this. I can fit an up and a down electron into that. And then I've got my n equals 2 orbitals, and there's 4 slots, and I can fit 2 electrons in each slot. So the degeneracy G is just 2 times n squared. Do you have a question, Chase?
Yeah. Can you do G2 on the top, or sorry, G1 on the top and G2 on the bottom for this problem because they're both 0.5?
Yeah, that'd be fine. But then you got to make sure you get, so that is going to introduce a sign error when you get to this point, when you take the log. So you just have to make sure that the sign on this matches the sign on this. So you just have to not screw up the order that you're taking. You have to not screw up the signs.
Okay, wait. Is G2 8?
Yeah,
Okay. Alright.
yeah. And G1 is 2. Okay, actually, let's handle this one. That'll be a lot more legible. Not legible, just more legible. Okay, does anybody have any questions on this one? Everybody happy? And then the last one, power. So the last one asked you to prove Kepler's second law, that planets sweep out equal area for equal time, and everybody did, I think, pretty well on this one, please. So I'll go through it uber quick. And so, let's see. So for this one, we said this chalk is, I don't want that. A bigger chalk. So this is largely a calculus stunt. dA, and I like to write this as d squared a because it makes more sense to me. This is the area element in 2 dimensions. It's just the polar area element. This is just r dr d theta. So then I then I integrate the dr, and I'm left with dA equals 1/2 r squared. That's just the integral of this guy, d theta. And then I divide by a dt, and I'm left with dA dt equals 1/2 r squared d theta dt. This is, I got 2 r's here, r times d theta dt is v theta, and r v theta is just L over mu. So this is just equal to 1/2 times the angular momentum over the reduced mass, which is a constant over a constant. So that means it is a constant. Some of you got to the bottom and then forgot to say that anything is conserved and didn't actually state why, didn't actually state the proof of the proof, which is this thing is conserved, so this thing is conserved, and that's what we're at. So I only knocked off a point for that, so you don't have to worry about it. Yeah.
For future reference, is it incorrect to use omega instead of v theta for this?
Yeah, omega and v theta are different.
Okay.
Omega is the angular velocity, and v theta is a linear velocity. The units are different.
Tangential?
Yeah, that's right. So this is the tangential velocity.
R omega is equal to the.
Yeah.
Okay.
Cool. So that was the midterm. We got it done in 13 minutes by not really spending very much time on it. Okay, so does anybody have any questions about that? Everybody did great. Where did they go? Because I noticed that Roberto came in. Humberto, I'm sorry.
Alright, I'm all late.
No worries. Denny, nobody else can in that right. Okay, so now I'm gonna finish up what we kind of started before. So we did Saha, and we did Boltzmann, and we did Maxwell-Boltzmann, and you read about using Boltzmann and Saha together, but I didn't really spend any lecture time on it because I kind of ran out of time and I wanted to get the midterm out. And this, I don't know, it's kind of hairy. So why do we go through this Boltzmann and Saha? What are we actually looking for? So what we're looking for, what we want to understand is these stellar spectra. Let's go back to that real quick. Did I put it here? Yeah, I did. So, okay, so they sorted out, from looking at the peak of the spectrum, they sorted out that this is how you have to sort them based on the temperature of the stars. But then we have these things that kind of come up and go down, which is how they were looking at things before. So they were looking at this Balmer line right here. Oh, my cursor is not overhead. My cursor's here. They were looking at this Balmer line, and they sorted it based on this Balmer line. But this Balmer line is not, like, it's gone up here and it's gone down here, but it's bright in the middle. So we want to understand this behavior. And so I'm going to pull up some plots from the book because they're nice plots. So that I can find it. And these are some plots that lots of people asked about. It's not anything to worry about. So let's talk real quick about Saha, and talk about what Saha is. I went too far. I want that plot, not that plot, not that plot. I want these two plots that are there. Okay. So let us change the camera. So I want to understand how many of the atoms. So how does a star work? Let's talk about that for a second. Let's get real big picture. So I've got a star, and at the center of the star, I have protons. I have protons that smash together and form helium. There are a couple of things. One's just smashing two protons together. Another one is there's this merry-go-round of carbon, nitrogen, and oxygen that you can get on and build helium that way. There's a couple of ways to do it, but there's nuclear burning in the inside of the star. And so what does it do? It gets really hot. Actually, it gets really hot, and then there's nuclear burning. It gets really hot because of the gravity. So you have all of this gravity that's crushing stuff in the center, and PDV work makes everything hot. You don't need to worry too much about that. What that, all this is for now, for us for the moment, all this is a heater. So that temperature winds around, and this is actually very small. This is this tiny bit down here, and then the sun is like this. These photons then wander around and heat up this bath of stuff. So now, I've got nuclear burning down here. So the nuclear burning is right in the center. And then the rest of the star is just hot. So this is very hot. This is just hot. I only gets one exclamation point. So this is hot. This is 1,000,000 degrees. And this is 1,000 degrees. Or 6,000 degrees, okay? So I've got this heater that's making this black body. Because it's just some hot gas, it makes black body. So the black body coming off so the radiation coming off the surface is a black body. So right here, we have a black body. And then I got this cloud of stuff. And what's in here? It's mostly hydrogen. And this hydrogen, so this black body gives us a spectrum that looks like this. And it's peaked at some temperature. So here's the visual band. It's peaked here, which is for the sun is in the green, but for another star it's somewhere different. Then I've got this atmosphere, and my photons all have to travel through the atmosphere. And some of them are going to get blocked by the hydrogen. So we need to sort out what fraction and at what frequencies the hydrogen is doing the blocking. So we want to sort out, let's just focus just on the Balmer line for a second. So I've got this, so this is the ground state, and this is a free electron, so this is excited. So this is the energy levels. So the first excited state is the ground state, and then the ground state is the ground state. 1 is the ground state. The first excited state is here, and then you have this chain of it's an infinite chain of levels that you can have. So I'm only going to absorb, so let's say the Balmer line is here. I'm going to absorb some photons from this region. I'm only going to absorb photons based on the density of states in this first excited state. I can't absorb something to this state if I don't have anything in the ground state, and I can't get things up into the first excited state. So I need to know how many atoms are in the first excited state. Okay, does that make sense? So what we have but what's going to happen, let's think about, I have a magic knob on this star, and I can just crank up the temperature. And we're just going to look at what happens to the Balmer electrons as I turn up the temperature. So there are basically 3 places that an electron can be. There's a continuum of places, but really they're all in the ground state for the most part until you start kicking them up. So when you start raising the temperature, they all start in the ground state. Then after a while, some of them are in the first excited state because you've got all this kinetic energy and it's smashing the things, and as they smash together, the electrons get excited. So it's the inelasticity of the system. So the other place they can be is off. So as I increase the temperature, they're also going to get kicked off of the atom. So I'm going to lose electrons off of my hydrogen atom. And that mostly comes from, that's the wrong graph. It mostly comes from the high-end tail of the Maxwell-Boltzmann distribution. So we've got these very high velocity atoms, and they have a lot of energy. So there's 3 places that I need to consider. There's the ground state. So there's the density of particles in the ground state. We'll call this N1. There's the density of particles in the second excited state. We're going to call this N2. And then there's the density of free electrons. We're going to call this, okay, in the book he calls this N Roman numeral 2 because that's what we call that hydrogen. So if I'm looking at hydrogen, hydrogen 1 with the Roman numeral 1 is neutral. Hydrogen 2 with the Roman numeral 2 has 1 electron missing. Hydrogen 3 would have 2 electrons missing, but that doesn't make any sense. Because I can't take another electron off of hydrogen. I can put another electron on a hydrogen, but I can't take another one off. So I can have something like helium 3, which would be helium with 2 electron removed. Or I can have iron 6, which has 5 electrons removed. So these Roman numerals just count the electrons that you've taken off. You don't need to worry too much about them because I'm not going to use them right now. I'm just going to call it 3 because it's so much easier for my brain. So 3 is a free electron, 2 is a bound electron, and 1 is a bound electron. So we need to know so we have all of these things that are ratios, Ni over Nj, and there are two such things that we described, and I'm going to real quick describe the Saha equation. We have Boltzmann equation, which I feel like everybody is pretty solid on. You have a question?
So when you have, like, say, a helium or like a lithium, would you have to consider more states?
The Roman numerals just are how many electrons are missing.
No, for the ends.
Yes, for other systems it gets worse.
Okay, that's, what I was wondering.
And it depends on the electron screening. So if you want to do this for helium, it works out pretty good, and lithium works out okay. For iron, it doesn't work out very well. So,
right. So as you get
Boltzmann still is true.
Mhm.
Boltzmann's still accurate, but I can't say that En equals some number times n squared minus n squared, n1 squared minus n2 squared. I can't say that anymore because the energy levels get a lot more complicated. They're not as simple as just n squared.
So just the heavier it gets, the more annoying it gets?
The more electron screening you get, the more annoying it gets. Heavier is fine.
Heavier's,
It's the electrons that are the problem. So if I have, so I have this energy, my energy levels go like some number times n to the minus 2. This is only true if there aren't any electrons in the way. If all I see is the central proton mass and then 1 electron, then it goes like n squared. These are called hydrogen-like atoms. So hydrogen is a hydrogen-like atom. Helium 2 is a hydrogen-like atom. Lithium 3 is helium 1 is helium 2 is a hydrogen-like atom. Lithium 3 is a hydrogen-like atom. So it gets, but the electrons in here make all of this kind of crappy. But
So-
Boltzmann and Saha still work. So the bulk still works just fine.
So if for some reason you had something that was super heavy with 1 electron, it would still work out?
Yeah,
Well,
that's
I don't
right.
know what system that would happen.
Well, if you have iron that's in, or oxygen that's in a galaxy cluster, the gas in a galaxy cluster is 1,000,000 degrees. So there you have a lot of hydrogen-like species in other weird species.
Huh.
So again, what we have are ratio equations. So we have Boltzmann, and Boltzmann, I feel like everybody's got their head around Boltzmann, but I don't think everybody's got their head around Saha yet. Mostly because I haven't really made you do it, so you can look forward to that in a future homework system. So I have the N2 over N, I'm going to call this I and J again, Nj over Ni equals Gj over Gi times e to the minus delta E over Kt. So this is Boltzmann. This is for this state, which is bound, and this state, which is bound. Now, it doesn't matter where I put my fingers. It's good for any pair of states. But the bound state. Because there's only one place for my electron to be in the third excited state, and that's in the third excited state. But how many ways can I have a free electron?
A lot.
A lot. Because I have my atom here, and then my electron is over here, and it has some momentum, P. And that's pointing in some direction. And that's whatever residual momentum that you have after you kick the electron off. So how do I get an electron off? I take 2 hydrogen atoms, I smash them into each other with more than 13.6 electron volts. If it's more than that, then the electron's going to come off and have whatever the difference is in energy. So the energy of this electron, of this free electron, is going to be chi This is the ionization potential, so for hydrogen it's 13.6 electron volts, plus 1/2 mv squared, just its momentum. Now, we like to think, or its energy, we would like to think about this as p squared over 2m. So this is the same as 1/2 mv squared. Can you see that? I got m squared v squared over 2m, so that's just 1/2 mv squared. So this is the energy that I need to consider for the upper state, but there's a bunch of them. This is a continuous now. There's a continuum of states. So now I have to do an integral. So I have to say, okay, this is good for this state versus this state, but now I want to do this state versus all of these states, so I need an integral. So we have this thing that looks like n, he calls it capital N, ni plus 1 over ni equals, let's see, how does the book write it? I'm writing it different from the book. The book uses partition functions. I'm just going to use the g function. Yeah, it gets you the same answer. Gi plus 1 over gi. For a free electron, that's 1. And then we have 2 over the number of electrons times this, 1 over the electron density, is the volume that one electron has to itself. Does that make sense? 1 over Ne is the volume. And then we're going to divide this by the de Broglie wavelength. So the de Broglie wavelength is exactly is how big the particle actually is. So we need to divide the volume of space I have for one electron by its de Broglie wavelength, and that tells me how much volume I need for each electron. Does that make sense? So the de Broglie wavelength is 2 pi mkt to the 3 halves over h cubed. So now you can think about this in a certain number of ways. So this is the de Broglie wavelength. So you can think about these two factors as the number of de Broglie wavelengths you can, or the number of electrons you can fit into a de Broglie wavelength, or the number of de Broglie wavelengths you can fit into one volume that I have carved out for one electron. And then I have this e to the minus chi over kt. So what happened in the middle is we did an integral over momentum. So I do an integral over momentum, which I don't care about, so I'm not going to do, and then I'm left with the Saha equation. So the Saha equation looks a lot like the Boltzmann equation, except the counting, this is counting. The counting is a little different because now I've got to count all of the free electrons instead of just one particular place. And the energy is a little different because this is now the ionization potential, not the energy difference. We took care of the energy difference. This is part of the energy difference. The rest of the energy difference we take care of in this integral. So hopefully you do Saha equation again when you get to statistical mechanics, because I think that seeing these things more than once is important. I'm just going to write it down and then not think about it too much. So I got these two equations now. And I'm just going to leave that up there and try to not write over it. I got these two equations that talk about ratios of states. But what I need to know what I'm trying to get at is how many Balmer photons do I have that can do this absorbing. So I need to know the ratio of Balmer photons, which is N2, these are the first excited state electrons, over the total, N1 plus N2 plus N3, the bound electrons. So this is going to be equivalent to N3 over N1. How I'm calling it this way. This isn't the ratio of two things, this is a ratio of four things, or three things, right? So we got to do a little bit of work. Nature doesn't give us any absolute densities or absolute number of electrons that makes any sense. So we always have to divide out the extrinsic quantities, like the total number of things. So that's why they're always pairs. So I need to turn this into a set of pairs. So I'm going to write this as N2 over N1 plus N2 times N1 plus N2 over N1 plus N2 plus N3. This is algebra that the book just totally skips over. Well, he says it in a sentence and then drops this weird equation that he doesn't explain. But that's all right. So this I can get at. I can get at this term because this only has 2 terms in it. This term I'm going to do a Taylor series on. And when I do a Taylor series, I'm not actually going to do it for you, but when I do a Taylor series, I can just cancel out the n1 and the n2, and I'm left with just n1 over n1 plus n3. n2 over n1 plus n2. Okay, now this isn't quite what I want. I'm going to rewrite these as ratios, and this is going to be n2 over n1 divided by 1 plus n2 over n1. That's this first term. I'm just dividing top and bottom by n2, or n1. And then I'm left with this other term, which I'll divide top and bottom by n1 again. And I'm left with 1 over 1 plus n3 over n1. So this is Boltzmann over 1 plus Boltzmann times 1 over 1 plus Saha. So this equation isn't something that you should memorize. This equation is something that you should memorize. This process of kicking out the little things is something that you should think about, but I'm not going to make you actually do anything like that. So what we need to do is we need to sort out what B is, and B is the ratio of how many things are in this state, and S is the ratio of how many things are in this state. So how many things are completely gone from the state. Does that make sense? What I did so far? So, does this make sense? Did Saha make sense? This is basically just, I got 2 states, but one of them is a whole bunch of states. So I had to do an integral and it gets uglier.
Okay.
But it's the same basic idea as this guy. Yeah.
So Ni is the number in the ground state, and then Ni plus 1 is, in this case, N3?
This would be N3, yeah.
Okay, but that's just any
Any
like the
pair
free
of
electron
things. Yeah,
state.
that's right.
Okay.
That's right.
So why is it written as Ni plus 1 if it's not always just like one more
I don't remember how he actually wrote it. I think he wrote it as that's the next ionization state. So I've got one ionization state, and that could be iron atoms with 9 electrons removed versus iron atoms with 10 electrons removed. Does that make sense?
Yeah.
So it's the difference between 2 ionization states.
Okay.
Does that come from like an induction proof?
No, you don't need to
Okay.
prove by
Well,
induction with that, but
No, I was just
But it's the
curious
same
'cause
idea.
that's the same idea.
it's the same idea. So I do it from the ground state and the first excited state, and then I know I can do it for any pair, so I know I
Okay.
can do it for everybody. Yeah, so yeah.
Oh, that very last term, was that an S or a 5?
The at the bottom,
Yes.
this is an S.
And
So
what's that
this is the Saha equation.
Oh,
This is N3 over N1. So that's this guy here.
oh,
So let me be clear. So this is Boltzmann, which is going to give me N2 over N1, and then Saha is going to give me N3 over N1.
okay.
And I got to do a little juggling to make sure that this makes sense. So what I'm looking at is N2 to everything. That's what I'm going for. I can't do that because I don't have, like, this is human beings lack the mathematical sophistication to do this. So we have to make it as ratios of things. So we do the ratios and we get to this uglier thing. So the form of this doesn't really matter too much. Think about this, and then we got to do some algebra to make it just into ratios. So then we go over here. So this first graph is the Saha part. So this is just plugging in this. So 1 is for a free electron, and the ground state is has a G of 2, and then the density of electrons is a free parameter. That's a knob. And the density of electrons is related to pressure. P equals NT times the Boltzmann constant. So this is just the ideal gas law. So we can rewrite this as a pressure. Think about that instead. And then the density goes away, and we're left with just a pressure. And we make this as a function of temperature. Temperature shows up here and here, and if we make this a pressure there, and then we plot. So these are all just numbers, and the ionization potential I know, so I know how to write this down for one electron coming off of one hydrogen atom. I've just got 1 and 2. This is a knob that I have. Temperature is the other knob that I have. Then H is a number, M is a number, chi is a number. And when you plot that, you get this plot up here. And you get that half of the electrons are are free at about 9,000 Kelvin.
And
8,000 Kelvin.
what is chi again?
Chi is the ionization potential. It's 13.6 electron volts. For hydrogen, it's 13.6 electron volts. For if you're doing this with something else, then it'll be whatever the ionization potential is for that last electron. Huh. So this is one of them, and then when I put N2 to N total, I get this. Why is that? So as I increase temperature, when I'm at real low temperatures, I can't kick anything into the second excited state. I can't ionize anything either. As the temperature goes up, I start kicking more things into the first excited state, and I start to ionize things. As I keep increasing the temperature, I kick things out of the first excited state, and they get ionized too. So the temperature, this is the fraction of ions that are in this first excited state, N2. And it goes up with temperature, and there's a peak around 10,000 Kelvin, and then it goes back down again. So it goes up because you're exciting the electrons, and then it goes up, and then it goes back down again because you overexcited the electrons. So it's like, this analogy of a toddler's birthday party. Toddlers are pretty fun, right? You get a little bit of energy, and they're really fun. If they have way too much energy, then the shit comes off the rails and all hell breaks loose, and your house burns down because it's all mayhem. So as you increase the mayhem, you get some Balmer electrons, and then you get no Balmer electrons. So this is why OBAFG is in this stupid order, in this plot here. That is something that I want you to make sure that you get your head around. I'm done for the day, so I'm going to stop. But we'll come back to this one in a homework. Oh, I should have changed the camera. Sorry for the listeners at home. Forgot to change the camera.
Okay, so the reason that it goes back down is because when you overexcite the electrons, the ones that are in that first back off, and
Yeah,
they're
they-
ionized and they're gone, and so there's less in it.
Yeah.
Okay, yeah. Okay.
And so you could do that graph by like
OBAFG?
yeah, could you do that like you do with the I'm sorry, this is terribly formatted.
It's okay, you'll get there.
You have the stellar diagram.
The HR diagram?
Yeah.
Yeah,
You
that
do
would
a
be
similar idea to that, but with
OBAFG.
okay. Okay, so that's so that's the really hot ones are like they don't have a lot of
Yeah, they don't have that guy yet. They don't have that guy.